The cube function looks like this. Okay, so we have the square function, which looks like this. Now we have the cube function that looks like this. It goes up to the right. I didn't write the equation of the cube function. F of x equals x to the third power. That's where it gets its nickname cubed. So 0, 0 is one of the key points that it goes through. It also goes through 1, 1, just like x squared did, but it goes through -1, -1 because it turns downward. It's like half of a parabola going up to the right and half going down to the left, kind of. What kind of symmetry does this graph have? It's an odd function, that's right, which is a nickname for what kind of symmetry? Symmetry across the origin. Very good. And you see that characteristic that where we had a point xy, we have also the point -x, -y on the same graph. Okay, so that's the parent function that you must memorize. Let's list our 3 key points. It's going to be 0, 0, 1, 1, and -1, -1. And whatever we do to this graph to create a new function, we will be changing those coordinates, repositioning them. So, for example, I might ask you to graph each function using transformations. Graph each function using transformations. We're going to do 2 on this slide. Part A, we're going to do g of x equals x minus 2 cubed. And part B, we're then going to do h of x equals x plus 2 quantity cubed. Notice that these are in parentheses. So normally you won't know that we're about to do a transformation of the cube function. I'll just ask you the question, and you'll have to look at the equation of the function and see the cube and say, oh, the parent function must be x cubed, right? So then you'll say, you'll sketch a little graph of x cubed real quick. You'll remember what the key points were, and you'll move them around. That's the procedure that you're going to use. But right now, you don't know yet, you're not familiar with all the different types of transformations. So let's talk about what effect subtracting 2 here is going to have.
Is that g x? Is that a g?
G of x, yes. All right, now, you see how that I'm subtracting 2, but it's on the inside of the parentheses there, as opposed to previously on the other side when I added the 3, it was outside of the square. This one is inside the parentheses. It's being affected by the cube. I call this the inner part of the function. Whenever there's an operation on the inner part of the function, and you'll get comfortable with what that means as we look at different types of functions, what it means to be on the inside of the function. But whenever it's on the inner part of the function, it's always going to affect the x coordinate in some way. Now, you might think that because we're subtracting 2 from the x, that we would subtract 2 from every x coordinate. That would seem reasonable. But unfortunately, whenever it's on the inside of the function, it kind of does the opposite of what you would think. But I can show you why. It's actually going to add 2 to every x coordinate. And here's an easy way to understand why. We're going to change the x coordinates, but we want the y coordinates to stay the same so that we know it corresponds to the original graph. So how can you get a y value of 0 out of that? What would you have to plug in for x to get a 0 out? 2, not -2, right? +2. So you see, right, that if you plug into g of x the number 2, you're going to get a 0 out. So what happens is the point 0, 0 moves to not -2, 0, but 2, 0. So in other words, it shifts which way? Where is 2, 0 compared to 0, 0? To the right, yeah. Let's go ahead and add 2 to each one of our x coordinates. So we're going to add 2 to the x coordinate. And we're going to get what? Instead of 1, 1, 3, 1. Good. Instead of negative 1, negative 1. If you add 2 to negative 1, what do you get? Positive 1, negative 1. That 3 looks a little weird. Let me fix it. Okay, so these are going to be the 3 new positions for those original key points. So we're going to draw our graph, and we're going to plot 2, 0, 2, 0. We're going to plot, instead of 1, 1, 3, 1, 3, 1. And instead of negative 1, negative 1, 1, negative 1. Okay, now isn't it interesting, if I just plotted those 3 points, doesn't that look like a line? Mm-hmm. So I get a lot of lines on the test. Okay, but what about this function tells me this is not a straight line? The cube. When you see the third power, you know it's going to look like f of x equals x to the third power. So it's going to be this squiggle shape. Half of a parabola up, half of a parabola down. How do you draw it? Again, don't try to start up at the top. A lot of times people start at the top and try to connect these, and I get just craziness. Okay, so it's much easier to start with the middle point, the 2, 0, and go up and to the right, kind of a little bit of a half of a U there. And then start at the middle again and go down and to the left. All right, so.
Also, that doesn't go straight down.
No, it doesn't become a vertical line. It's going slightly out all the time. Okay, so what we saw is that when we performed an operation on the inside of the function, it affects the x coordinates. And since we subtracted 2, when we have a negative, it shifts it to the right. Shifts right. What do you think is going to happen in part B when we have we're adding 2? It's going to shift to the left. That's right. So for part B, we're going to write down our 3 key points. It's still the same parent function that we started with, f of x equals x cubed, which contains 0, 0, 1, 1, and negative 1, negative 1. But we know that we're changing the x coordinate and we want our y coordinates to stay the same. The only thing we could plug in to get a 0 is what? Negative 2. So that's your little clue there that we're subtracting 2 from every x coordinate. So we're still affecting the inner part of the function. It's still going to change the x coordinate. And since it's plus, we're going to shift to the left, which means we're going to actually subtract 2 from every x coordinate. Subtract 2 from the x coordinate. So instead of going through 0, 0, it's negative 2, 0. Instead of going through 1, 1, subtract 2 from the x, and what do you get? Negative 1, 1. The y stays the same. How about negative 1, negative 1? What happens if you subtract 2 from the x coordinate? Negative 3, negative 1. Okay, so I'm going to graph it on the same axis that I just did part A. That was the graph of G in blue. Let's go ahead and graph H in green. So I'm going to go through negative 2, 0. I'm going to go through negative 1, 1. And I'm going to go through negative 3, negative 1. Again, if you didn't know that you were graphing a cube function, that would look like a straight line. But we know that that negative 2 was that special point. By the way, what's special about the point 0, 0 in this original function here? Does it change from increasing to decreasing? No. But there's definitely a change, isn't there? You see how before the 0, 0 it's curving downward, and then after the 0, 0 it's curving upward. So on the right it's like it could hold water, and on the left it's like it would pour it out. That's called the concavity. You don't need to know that, but if you take calculus, this is a point where it changes from concave down to concave up, and that's going to be important when we want to know the shape of a graph. So it's very important that as you're drawing these, that you reflect that in your drawing. I want you to understand the shape is significant. So if any of you do go on either the business calculus or calculus route, you're going to be great graphers. Okay. So we're going to make sure that you start at -2, 0, go up and to the right, and then start at -2, 0 again, go down and to the left, making sure it looks curved the right direction. Okay? All right, both of these, the graph of G and the graph of H, are a horizontal transformation, a horizontal shift. One shifted to the right 2 units, and then we had the other one shifted to the left 2 units, but they both were horizontal shifts. And you can do this with any of the parent functions. You can use them to shift them around to get new functions.